Hello students, welcome to optional advanced topics in linear algebra. The purpose of this lesson is to discuss the algebraic rules in regards to matrix multiplication. We're talking about these rules, and this is the definition of the matrix multiplication. Now, in terms of computation, everybody went through several exercises by now, so you'd know what you're doing. Basically, we do these kind of computation. First row, first column. Take the scalar product of it, and we get 1, 1 entry. First row, first column. First row, second column. We take the scalar product, and what do you get? We get 1, 2 entry. First row, second column. We're done with first row, so let's go to second row, first column. That is the scalar product computation, so consequently we get 2, 1 entry. Second row, first column, and so on and so forth. And that's how you do the computation. But in theory, we have to work out in general setting with all those characters and indices, so it's a little bit harder to understand. Nonetheless, we must do it. So let's go over these. So matrix A is m by n matrix, m rows and n columns. Matrix B is n by p matrix, n rows and p columns, So that the scalar product, this row vector, and then the column vector will be well defined. They're both n-dimensional. As you can see in the scalar products computation here, goes up to n. Okay. That is a little bit easier half. How about the other half? Look at the indices. Aij, so ith row, jth column, and bjk, jth row, kth column. And j is changing from first, second, third, all the way up to n. First, second, third, all the way up to n. Now let's look at this scalar product computation. First, second, third, fourth, fifth, in the end, n. So j is going from 1 through n. So we have to have same j here, same j there, and then the ij, jk, these are same, and then j is moving from 1 through n. In the end, what happens? The common index j disappears, because what happens in the end is ik entry of the product matrix. So, two important numbers here. N, that's the size of these matrices, number of columns for the left, number of rows for the right. That's one. Another one, J, the index J equals 1 through common size N. Those two numbers are very essential in the definition of this matrix multiplication, and they're common, and as I highlighted in red. But in the end, they both disappear. It's kind of ironic, isn't it? The most important characters that define the matrix multiplication and make those matrix multiplication valid disappear in the end. Keep this in your mind, and then let's go to the first proof, the associativity. Okay. Here is the proof. Let's calculate the left-hand side first, and then calculate the right-hand side later and compare them. Are they going to be the same? Let's see. How about the left-hand side? Let me copy and paste this thing. And then the left-hand side, let me highlight in red. And then let me highlight this one in blue. Okay, alright. Let's pay attention to red first. A times B, because that's done first. Look at this. Matrix A times matrix B was done first. They're inside the parentheses. And how was it defined? M by n matrix, n by p matrix, n is common, so mn and p. So in the end, we get m by p matrix. Okay. Now let's look at the indices. Aij, Bjk, Ij, Jk. J's are common, so we end up with Ik entry. And what is the Ik entry? It's a scalar product. J is running from 1 through n. The summation is always the case. And Ij, Jk, they collide and cancel each other out. Ij, Jk. So all the red part here are essential in the definition, but in the end, they disappear. Okay, after they disappeared, this whole thing is what? Ik entry. As we saw in this example, okay? This is Ik entry. But we need another multiplication, right? So Ik times now KL. Remember, we have to have same index coming. So this is Ik. So KL. K is common this time. So IJJK gave you Ik. And then now IKKL will give you IL. And how about the size? MP and then PQ. MP, PQ, we get MQ. And how about the summation? Well, this whole thing was there before, so it's reproduced here as I just highlighted. And then this is Ik entry, right? So K here and K there are common. So this whole thing I just highlighted is actually Ik. So Ik and then KL. Total, we have IL. Or if I put everything together, IJJK, KL. So we have IL. IJ, JK, KL. So we start from I and in the end we have L. So IL. The most important terms here, the most important indices, J's are common, coming from the first computation, and K's are common, coming from the second multiplication, which are red and blue respectively. They must be the same, but in the end they all disappear, and we get just IL. Now how about the right-hand side? It's very similar, but we do blue computation first, BC first. So how are they calculated here? NP, PQ. NP, PQ. So in the end we get NQ. Okay, that's the size. And the other half, JK, KL. JK, KL. And K's are common, so we have JL. You see? You have to have same indices K and K and the same size P and P in order to have a well-defined matrix multiplication. But in the end, they both disappear. This expression here is actually JL entry. K's are common, they collide and disappear. This is JL. JL. Okay, JL, all right. And previously we had IJ. So IJ, JL. IJ, JL. J's collide and cancel each other out. How about sides? MN and Q. MN and Q. N's collide and cancel out. What do you get? A matrix, product matrix, MQ, M by Q. You see, MN and Q. Or MN and P, PQ. In the end, we get MQ. And then look at all those indices here. Let's see. This part was done first. JK, KL. So in total, we have JL. And then IJ, JL. So J's cancel out. This whole thing is actually L. The whole thing is IL entry. And we already had the summation, so we have the second summation there. So, did you get the same thing here and there? Very close, but looks like there's one little difference. The order of the summation, those two are different. Do they make difference? Well, that's a little bit deep story, especially in analyses. And in analysis, they're not always the same, and that opens up really huge floodgate. But that's analysis, because in analysis, we deal with infinities. But here, in linear algebra, especially at this level, everything is finite. And addition is commutative and associative, especially associative in this case. So it does not matter which bracket you calculate first and which bracket you calculate them later. As a matter of fact, this is a kind of array of all kind of additions in rectangular order. And then whether you calculate each rows first and add them later, or each columns first and add them up later, it's the same deal. It's an associativity of addition in real number arithmetic in action to give you these two are equal. That can get a little bit long and tedious if you want to write everything down in detail. So I'll just explain those as associativity of real number arithmetic, and that's it. And of course, we are trying to prove associativity of matrix multiplication. So at some point, real number arithmetic or its corresponding property in real number arithmetic may come into play. So that's not surprising. What is a little surprising here is associativity of addition came into play in addition to associativity of multiplication of real numbers too. Anyway, here we go. Tricky, so let me try to explain it just one more time. So here, red first. How do you do red? Well, size first. Mn and P, m by n and by P. We have to have same n's here. Number of columns, number of rows, they have to be the same. Otherwise, multiplication is not well defined. But once they are well defined, in the end, they disappear. We have MP. So ith row, jth column, jth row, kth column. J must be common. One row, one column. Same index J. But after well-defined scalar product, they both disappear. And then what do you get? We get IK entry. So okay, we have IK entry and KL entry. IK, KL. Total, we are going to get IL entry. Ith row, lth column. And then how about the size? MP, PQ. So we get matrix of M by Q. So MN and Q, no. MN and P, PQ. Okay, kind of like this. MN and P, PQ. And then these kind of cancel each other out. That they don't really look like canceling each other out. Shall I write like this? Oh, this doesn't look good. These are not really algebraic operations. Anyway, that's how they collide and cancel each other out. So do the indices. Indices J, J cancel each other out, and we ended up with IK entry. And then our K, K canceled out, we get IL entry. How about the next one? We have to do this blue computation first. So matrix size NP, PQ. So we get NQ. And how about the indices JK, KL? So we have JL. And then combine that with the first matrix, IJ, JL. So we end up with IL. So this is IL, that too is IL. And then if you look at each individual multiplication, IJ, JK, KL, IJ, JK, KL, they're all the same. And the summation, they don't matter. They're always the same. So we have the same result here and there. Okay, so much for associativity. And do I have enough time for one more?